Hello viewers, we're taking you through the story for A-level physics paper 1, and this video I'm going to go through the topic of dimensions of physical quantities. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. Before we start, let's just look at the course outline of this paper of physics paper 1. So physics paper 1 is divided into three parts. The first part is heat, the first part is mechanics, where 4 questions come from these topics. The second part is heat, where 3 questions come from these topics. And the third part is modern physics, where 3 questions come from these topics. So the whole of modern physics is complete, and part of heat is complete. What is strict is what is available. But now we shall first pause a bit with these ones and first deal with some topics in mechanics. So in this video, I'm going to go through the first topic of mechanics, and that is dimensions of basic and physical quantities. Here we are interested in the calculations, but complete notes are available in the book Mastering A-level Physics paper 1. So it has the entire mechanics, heat and modern physics, both notes and worked examples, and also trial questions. So for orders of this book, contact the author on any of these 2 contacts. So physics, there are 3 books, that is physics 1, then there is also physics 2, and lastly a topical question bank. The same applies to principal math. There is math part 1, math part 2, and a topical question bank. So for any of the copies, contact the author on those contacts. So let's start our topic of dimensions. So by definition, dimension of a physical quantity is the way that given quantity is related to the basic or fundamental quantities. So there are 3 basic fundamental quantities, so they can call them basic quantities or fundamental quantities, and those 3 are mass, length, and time. And the dimensions of any quantity is noted by a box bracket. Note that we use only and only a box bracket. So if I say box, if I put a box bracket and I put inside A, it means I want to get the dimensions of A. Therefore, this, if I put here mass and I put in box bracket, it means I want to get the dimensions of mass. So let's start with the dimensions of basic quantities. Remember, there are 3: length, mass, and time. So by definition, a basic quantity is a quantity which cannot be obtained from any other quantity. So mass cannot, length cannot, and time cannot. So those are the 3 basic quantities so far. And their dimensions include the following. So mass, the dimension is capital M, and the unit is kilogram. Yes, our unit is kilogram. Length, the dimension is capital L, the unit is meter. The time is capital T, and the unit is second. And it's from those basic quantities that we get all other dimensions. So the other dimensions, we call them derived. The other quantities, we call them derived quantities. So their dimensions can be got from a combination of basic quantities, as we are going to see. So derived quantities, by definition, are quantities which are obtained from basic quantities, and these include the following. So we have a number of them. So area, the SI unit, because this is the first topic in Senior 5, we shall remind ourselves of the SI units, but our interest is the dimensions. However, we shall talk about the SI units because they are somehow related to dimensions. So the SI unit of area is square meter, which is this in symbol form. And this dimension, it means that meter, remember we said meter is the SI unit of length. Therefore, if you see meter squared, it means the dimension of area will be capital L squared. So this is what I told you, that the SI unit will help us in this first topic of ours because they are related to dimensions. If you see meters, just know the dimension will be length. If you see second, just know the dimension will be time. If you see kilogram, just know the dimension will be mass, like that. So here the dimension. So here we are saying meter, meaning the dimension will be capital L. It is m squared. That's why here it is L squared. So what about volume? For volume, the SI unit is cubic meter. Therefore, the dimension will be L cubed. Like that. So you can see there is a relationship between the SI unit and the dimension we want. So once you know the SI unit, then this topic will be easier for you. So density, the SI unit is kilogram per cubic meter. Therefore, the dimension will be kilogram is capital M and per cubic meter is L to power negative 3. But how is it got? It is got by saying density is mass over volume. Mass is capital M, volume is L cubed, to give you this. So you can choose to go through these steps, or you can choose to just get it from the SI unit and say kilogram is mass, which is capital M, and meter is length, which is capital L. Then you put this power negative 3, and that is all. So any of the two is okay, because our interest is getting this for this. When it comes to the velocity, SI unit is meter per second. So meter is length, second is time. Therefore, the dimension will be capital L, capital T, and power negative 1. So once you know the SI unit, then the rest will be easier. Let's go to acceleration. Now what we are doing, we are looking at a number of derived quantities which are common in physics paper 1. Acceleration, the SI unit is meter per second squared, or per square second, which is L t to power negative 2. Therefore, the SI unit will be L t to power negative 2. Then force, the SI unit is Newton, or kilogram per square second, per meter, kilogram meter per square second. But how is it got? Force is mass times acceleration. Mass is m, which is kilogram, and acceleration, remember we already saw acceleration here, it is L t to power negative 2. So when you combine, you get the dimension for force, m L t to power negative 2. So now we shall go to pressure. Pressure, the SI unit of pressure is Pascal or Newton per square meter. And the Newton, the dimension for Newton is this. Remember, force was Newton and its dimension was that. So it will be, this will be for N, and for M it will be L to power negative 2. But if you want, you can get it from force over area, where force is this and area is L squared. I think remember the dimension for area. Then from the laws of indices, when this one goes up, it becomes L to power negative 2, but there is also L to power 1. So L to power 1 times L to power negative 2, you same base, you add the powers. So 1 minus 2 gives you negative 1. That is why you're seeing here negative 1 on L. Then we shall also look at work. So work, the SI unit is Joule or Newton meter, and Newton, you are already seeing the SI unit, the dimension of Newton is this, and meter is capital L, to give you that. Then energy, it is the same thing because all are joules. so the SI unit will be the same, so the dimension will be the same. Then power is work done over time, so it will be work done, which is this, and over time, which is T, to give you this. Then momentum is kilogram meter per second. Remember, momentum is mass times velocity, so mass is kilogram, velocity is meter per second. So it will give you this as its dimension. So there are a number of dimensions, but those are some of the few. The good enough you have understood how you can get the dimensions of derived quantities from basic quantities. So now we are going to go to what we call uses of dimensions. There are three uses. One is to test for consistency of equations. I can tell you to show, like for example, you see this question, show that the formula is dimensionally consistent. So dimensions are used to test consistency of equations, and two, they are used to derive units of physical quantities. So that is the reason why I was giving the topic is about dimensions, but I was also giving the SI units so that you can see the relationship. So the relationship between units and dimensions, because if you have the units, if you have the SI unit, you can easily know the dimension, meaning that the reverse is true. If you know the dimension, you can get the SI unit, as we shall see in this video. Then the third use is that it is used to find the units of unknowns in an equation. For example, they can give you this equation and they can say, find the SI unit of this. So that is also a work of a dimensions. We shall look at all these three in order. So let's start with this first one, where it is used to test consistency of equations, and that is case 1. So question 1 came from UNEB 1997 paper 1, question 1A, and says that centripetal force capital F required to keep a body of mass capital M moving in a circular path of radius r is given by this formula, F equal to mv squared over r. Show that the formula is dimensionally consistent. Dimensionally consistent means the dimensions on the left hand side are equal to the dimensions on the right hand side. So we shall deal with each side and see if they are equal. So like I told you, if you want to get the dimension of F, you must put it in box bracket. Always remember that. The dimension of what you want to get, put it in a box bracket. In physics, you shall know that you want to get its dimension. So I want for here, for this, and for this is that. Then after getting the dimensions, don't put in box bracket. I think you realize that now here, I'm putting it in a curved bracket. Here it was a box bracket, but here it is a curved bracket because I have already got the dimension of V and it is this. If by mistake I put this in a box bracket, it means it is not okay, because it will mean that I want to get the dimension of capital L and the dimension of capital T, which is not correct. So always be keen on the brackets you use. The box brackets are used before getting the dimension. Then after getting the dimension, don't use a box bracket. So the dimension of force is here. We are good enough. You have already looked at these dimensions. You can go through the previous slide. So force, we already saw it was that. Mass, it is capital M. Velocity, it is that. It is squared, that's why you put this power. Then radius, it is length, which is that. Then next is to use the laws of indices. Laws of indices are first open brackets. This is L squared, and this with this gives you t to the power negative 2. Then 1L cancels with this one to give you M L T to the power negative 2. I think realize that they are on each side, they are equal. Left hand side is equal to right hand side. And when that happens, it implies that the formula is dimensionally consistent. That was question 1. Now we shall go to question 2. Question 2 came from U.A.C.E 2005 paper 1 question 1b, and it says the equation of volume V of a liquid flowing through a pipe in time t under steady flow is given by this formula, where r is the radius, p is the pressure difference between the two ends of the pipe, L is the length of the pipe, and this symbol is the coefficient of viscosity of the liquid. Now, of these symbols, what we don't know is this one for coefficient of viscosity of a liquid, and that is why in this question it has been given. So if the dimensions of this is this, so if the dimension, in other their meaning, if the dimension of coefficient of viscosity is m L to the power negative 1 and T to the power negative 2, show that the above equation is dimensionally consistent. So they have only given you the dimension for this, meaning that these ones, they expect you to know them. So even this one along the way, you'll understand what it means, but for now, because this is the first topic in your senior 5, you don't need to know it, and that is why it is given. So it is assumed that you don't know it, but these others, it's assumed that you know it based on your knowledge of senior of O level. So let's go through the steps we used in question 1. First, we shall code the formula, then we put it in box bracket. Each term is put in box bracket. Okay, this is volume, this is time, this is a constant, this is radius, this is pressure, this is coefficient of viscosity, and this is length. So you come and put the dimension of each. For volume, it is L cubed. For time, it is capital T. A constant, so as long as there is a constant, you just put 1, because a constant is dimensionless. Radius, it is capital L. Pressure, I think you remember this, we derived it already. Coefficient of viscosity, it was given in the question, and length, it is capital L. Then now next is to use the laws of indices. This one becomes L cubed T to the power negative 1. Then the one up, there is 1m. Then this L to the power 4 and L to the power negative 1, 4 minus 1 is 3, that's why there is L cubed. Then this is T to the power negative 2. Then for the denominator, there is m. This and this cancels because L to the power negative 1 and L to the power 1, 1 minus 1 is 0. That is why there is no L here. Then T is to the power negative 1. Then again, further laws of indices, this cancels with this, and this one, when it goes up, it becomes positive 1. So negative 2 plus 1 is negative 1, that's why you see negative 1 here. And the good thing, the left hand side is equal to right hand side, implying that the equation is dimensionally consistent. Question 3 came from U.A.C.E 2010, paper 1, question 4D, and it says, the velocity v of a wave in a material of Young's modulus E and density rho is given by this formula. Show that the relationship is dimensionally correct. So still we shall come and quote the formula, then we substitute. Velocity, dimension of velocity is that. Young's modulus, the dimension is this. So this one was also supposed to be given because at this point you don't know it. Then the density you know it, so it is that. So Young's modulus here, I forgot to put it there, but it is supposed to be given in a question at your level. But as you progress, it will not be given. Like in this year, it was not given because It was assumed, it was known that student had already covered Young's modulus. Okay, then laws of indices. Laws of indices, this cancels with this, then this one goes up. 3 minus 1 is 2. That is why you see a positive 2. Then t to the power negative 2. Then that power enters, so 2 times a half is 1 and negative 2 times a half is negative 1. So it is still left hand side equal to right hand side, meaning it is dimensionally correct. Question 4 came from U.A.C.E 2001 paper 1 question 4a, and it says the resistive force on a steel ball bearing of radius r falling with a speed v in a liquid of viscosity this is given by this, where k is a constant. Show that k is dimensionless. In other words, they want you to show that k has no dimensions. Now here you realize that I've not given you the dimension of this coefficient of viscosity because in question 2 it was already given 2 or 1, question 2. So I don't need to again give it. I assume that now you know it. So make k the subject. You come up with that. Then I want the dimensions, so I put in box bracket. And force, that's the dimension. Quantity of viscosity, we know it. Radius is that, and velocity is that. So next is laws of indices. You come up with this, and everything cancels to remain with 1. Because I'm getting 1, it means k is dimensionless. So that was one use of dimensions. Shall go to the next second use, that is case 2, where dimensions are used to find unknown indices in the given equation. So this is done by equating indices of the same fundamental dimensions on both sides. As you shall see, so question 1 came from U.A.C.E 1999 paper 1 question 2b, and it says the viscous force on a small sphere of radius a falling with the velocity v in a liquid of coefficient of viscosity this is given by this expression, where k is a dimensionless constant. Use the method of dimensions to determine the value of x, y, and z. So you shall remember that we equate the same fundamental dimension on both sides, the indices. So we want to get the dimensions of each. So for f, k dimensionless is 1, a is radius, which is that, and coefficient of viscosity, then velocity. Then we shall use the laws of indices to collect like terms. There is L to power x, there is L to power negative y, and there is L to power z. Then for t, there is t to power negative y and t to power negative z. M, it is only 1, m to power y. So we said you equate the indices of the fundamental dimension. So for m, we can equate with this. Here there is m to power 1, here there is m to power y, meaning that the indices are 1 equal to y, therefore y is equal to 1. Then when we come to t, here there is negative 2 and here there is negative y minus z. So you can equate negative 2 to negative y minus z. And we know the dimension of y, so come and substitute and get the value of z. Then for L, so when I equate the dimension indices of L, I'll come up with this. L here it is 1, here it is this. So substitute for z, for y and z, you come up with x as that. And those will be the values they wanted. Then question 2 says the maximum power P developed by the wind turbine is related to the blade radius r, driving wind speed v, and density of air sigma. Derive the expression for maximum power using the method of dimensions. So let P be in this form, because they said P is related to R, so it is R to power X because we don't know the power, related to V, so V to power Y, we don't know the power, and density, which is sigma to power Z, because we don't know the power. Then shall guess the dimension of P is that, R is that, V is that, and sigma is that. Then we shall come and get the dimension for this equation here, which are these: P, R, V, sigma. Then use the laws of indices, collect like terms of M, L, there is L here, L to power X, L to power Y, and L to power negative 3Z. For T, there is just T to power negative Y. So equating indices of M, here it is 1, here it is Z, therefore Z is equal to 1. Then indices of T, here there is negative 3, here there is negative Y, therefore Y is 3. Then for L, here there is 2, here there is X plus Y minus 3Z. So substitute for Z and Y and get the value of X, and that's what they wanted. So they told you to at the end to derive the expression, so it means that this X will be put here, this Y will be put here, and this Z will be put here to come up with that formula. Then using dimensions to find units or dimensions of unknowns in a given equation. So here units or dimensions of unknowns in a given equation can be got by using the concept that when two quantities are added or subtracted, they must have the same dimension. So when I say addition or subtraction, it means that those quantities which are being added or which are being subtracted must have the same dimensions. And let's see how that concept is used. In question 1 came from Geneva 2002, paper 1, question 1a, and it says, for a streamline flow of a non-viscous incompressible fluid, the pressure P at a point is related to the height h and the velocity v by the equation this. Okay, where a, b, and d are constants, and rho is the density of the fluid, g is the acceleration due to gravity, and d is the acceleration due to gravity. Given that the equation is dimensionally consistent, find the dimensions of a, b, and d. So here these two are being subtracted, meaning the dimension of P is the same dimension of A. Okay, these two are being subtracted, meaning the dimension of H is the dimension of B. These two are being subtracted, meaning the dimension of V squared is the dimension of D. And remember, they told us P is pressure, so A is equal to have the same dimension as those of pressure. H is height, meaning B has the same dimension as height. And V is velocity, meaning D has the same dimension as velocity squared. So let's do that in this next slide. So A has the same dimension of pressure, which is that. Then B has some dimension of height, which is that. And D has some dimension of velocity squared, which is that. And that's what they wanted. So in case they wanted SI unit, it means that for A, M is kilogram, L is meter, and T is second. So this will be the SI unit of A. Then for B, it is just L, which is meter. Then for C, it is L, which is M, meter, and T, which is second. So this will be the SI unit of D. Question 2 came from UNEB 2016, paper 1, question 1A, and it says, in the gas equation, this P is the pressure, V is the volume, T is the absolute temperature, and R is the gas constant. What are the dimensions of the constants A and B? So you still use the same concept. As long as two quantities are added, they have the same dimension. So this P has a dimension which is equal to A over V squared. That's why I say here that they are equal. Then when I make A the subject, this one goes this side to come up with this. Then put the dimension of P, dimension of V squared to give you this as the dimension of A. Then for B, dimension of this is the dimension of V, which is L cubed. And that's what they wanted. So in case that's for SI unit, you look at this M, which is kilogram, meter, second, and that will be the SI unit. For this, it will be meter cubed. Question 3 came from UNEB 2002, paper 1, question 2A, and it says, two alternative units of gravitational field strength are this and this. Use the method of dimensions to show that the units are equivalent. So you have put the word edited because in the question they had put here meter per second, which was wrongly set. It was supposed to be meter per square second. So the dimensions of this unit, Newton is force, kg is mass. So force is that, mass is that, to give you this. Then the dimension of meter per second squared, meter is length, per second squared is time squared, which gives this. So they are the same. Question 4 came from UNEB 2002, paper 1, question 2A, and says, the velocity v of a wave of wavelength lambda on the surface of a liquid of surface tension this and density this is given by this, where g is the acceleration due to gravity. Show that the equation is dimensionally consistent. So yeah, still for your level, this dimension was supposed to be given because you have not yet covered surface tension to the detail. So you come and quote the formula, then get the dimension of each. Dimension of v squared is that. The dimension of this is this. So lambda wavelength is that, acceleration due to gravity, and a constant to give you this. Then for this one, we shall come and substitute 2 pi is a constant. Now surface tension, they were supposed to give you this dimension. Then wavelength is that, density is that, to give you this. So I think you realize that this dimension and this dimension and this dimension, all of them are equal. This, and this, meaning that it is dimensionally consistent. So previously we have been using left hand side equal to right hand side, but now in this case, as long as there is a plus, it means that these two must have the same dimension. Then question 5 says, show that the expression this is dimensionally consistent, where v is the final velocity attained by a body that starts moving with a velocity u, covering a distance of s, when uniformly accelerated at a meters per second. So yeah, the dimension of v squared will be that, then u squared will be that, and 2as will be that. So they are all the same, meaning it is dimensionally consistent. So that is how they deal with showing that an equation is dimensionally consistent when there is a plus or a minus. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on motion in a straight line. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.